Okay, so when we have a function f of x equals b to the x, this is going to be invertible because either these functions are always increasing or they're always decreasing, so they don't repeat y values. So they always have inverses. These inverses are written in this way: f inverse of y equals log with a little b of y. The b tells us the base of the exponent. We say this is the logarithm with base b. Okay, so if we have b to the x equals y, and we know y, then the solution x is our logarithm. So log base b of y is telling us the x value, so that b to the x gives us y. Okay. So we have that the log base b of y equals x exactly when b to the x equals y. And we can translate between these two formats. This is the logarithm form, and this is the exponent form. And the logarithm really answers the question, b to the what gives me y. So the output of the logarithm is this exponent. All right. And one common strategy for solving these for figuring out values of logarithms is, when we have a logarithm question, to just convert it over to our exponential form. So for example, here we have the log base 2 of 8. We can rewrite this in exponential form by saying 2 to the what gives me 8. And rewriting 8 is 2 cubed. So the log base 2 of 8 is equal to 3. It's telling you the exponent that we need when our base is b to give us that b to that exponent is 8. Okay, let's try out another example. All right, we are going to find the log base 10 of 10,000 by converting it to exponential form. So what we're asking is 10 to the what is equal to 10,000. And rewriting 10,000 as a power of 10, well, we see 1, 2, 3, 4 zeros, so this is 10 to the 4th. So the log base 10 of 10,000, or 10 to the 4th, is going to be equal to 4. Fabulous. All right. So here we have a couple of other examples. I'd like you to take just a minute or two, pause the video, and let's try out a couple of them. So the way that we can think of filling this out is we are going to be interested in knowing the log base 10 of 1, for instance. And in order to do this, we're going to convert it to exponential form. So this is the same thing as saying 10 to the what gives me 1. We know 10 to the 0 gives us 1. And so the log base 10 of 1 is equal to 0. Okay. Let's take a look at another one. If our input is 10, the log base 10 of 10, we're going to rewrite it in exponential form. So we're saying 10 to the what gives us 10? Well, we know 10 to the 1 gives us 10. And so the log base 10 of 10 is equal to 1. All right, pause this and try and fill out the others. Okay, so we should come away with something like this. So there was a little typo here. It should have said 1,000 instead of 10,000. Okay, so we see that the log base 10 of 1 is 0. The log base 10 of 10 is 1. The log base 10 of 1,000 is 3. The log base 10 of 1,000,000,000 is 9. Okay. So we see this function grows. We know that its range is going to be negative infinity to infinity. But boy, is it ever slow. This is a very slow growing function. Our output isn't 9 until our input is 1,000,000,000. So the logarithm is just telling us what power of 10 we need to write our number. So for example, 1,000 is 10 cubed. And so the logarithm base 10 is just 3, that cube. So we don't quite know how to write this yet, but take a stab. The seconds since the Big Bang are estimated to be about 4.35 times 10 to the 17th. So take a quick stab. What do you think approximately is the log base 10 of the number of seconds since the Big Bang? All right. So what we're going to find is that this is, so we see this 10 to the 17th. This is going to be somewhere between 10 to the 17th and 10 to the 18th. So we expect this to be somewhere between 17 and 18. And we will look at this a little bit more soon. But we see this is a really slowly growing function. And let's take a look at, we've got all of these values. Let's build a quick sketch of this graph. Okay, so remember that our domain is going to be values that are more than 0. It's a little longer. Okay. Okay. So, well, we said that because 10 to the 0 is equal to 1, that means that the log base 10 of 1 equals 0. We are always going to have this x-intercept of 1. We know that 10 to the first power is equal to 10, so the log base 10 of 10 is 1. Okay. We know that 10 to the negative 1 is equal to 1/10. So the log base 10 of 1/10 is negative 1. Okay, so this is going to get really close to, but doesn't quite cross that line, x equals 0. This guy is growing. It's going to very, very, very slowly, as x goes to infinity, our y values will eventually get as large as we like them to get. It's going to take a long time. Okay. So, but we can point out that here we have this x-intercept of 1, 0, and this here is the point, 10, 1. Okay. So let's do a quick rundown of the information about this function. So if we have f of x equals log base b of x, where our b value is greater than 1, its domain is going to be 0 to infinity. Its range is going to be negative infinity to infinity. log base b of 1 is always 0, and the log base b of b is always equal to 1. It has no breaks or jumps in it, so it's continuous. It does have a vertical asymptote of x equals 0. This is a vertical line that our graph gets close to. We get really close to this vertical line here at x equals 0. It has no horizontal asymptotes, no horizontal lines that it gets close to. This is always going to be increasing if b is greater than 0. And it is invertible, right? This, if we draw a horizontal line across it, we see that we're only going to touch in 0 or 1 spots. Okay, great. Next up, we're going to look at some properties of these logarithms.